You have acquired the basic science tools required to understand and navigate the rest of this book. We turn to the second part of this book, which is the experimental tools of nanoscience, chapters 4, 5, and 6, and in particular, chapter 4, which covers microscopy and manipulation tools. We begin by talking about the scanning probe microscopes, the scanning tunneling microscope, and atomic force microscope. We discuss force measurements on single molecules. We discuss various other AFM modes, both of imaging and measuring. We discuss electron microscopy, single molecule fluorescence methods, and then finally tweezers for manipulating single molecules. On the historical side, I begin with a discussion of the scanning tunneling microscope. In the broader perspective of nanoscience, the scanning tunneling microscope is a fairly obscure tool, but it was really what brought nanoscience into the public consciousness. We understand how scanning tunneling microscopes work because we discussed the very sensitive distance dependence of tunnel current in chapter 2, and we know that for a typical work function phi here of say 5 electron volts, this expression says that the tunnel current will decay by an order of magnitude for every angstrom that we change the gap between a conducting probe and a surface, and therefore as we move a probe over a surface we can map it at atomic resolution. This image on the left is a page from Gerd Binnig's laboratory notebook at IBM Zurich. What he does at the bottom of the book is the page is to calculate if one takes a probe of radius 1 micron, so a very blunt probe, but calculates where the tunnel current comes from it. Most of it is localized because of this exponential dependence to an area that's only about 45 angstroms in extent. So Binnig realized that he could use a fairly blunt and therefore stiff probe, but still achieve high resolution. Just how high was a surprise, because it was shown early on that in fact atomic resolution on surfaces was readily achievable. This beautiful image here taken by Don Eigler at IBM shows a circle of iron atoms that have been pushed into position using a scanning tunneling microscope probe. The atoms were evaporated onto a very cold metal surface, and here you see the metal atoms on the surface. But inside the ring of iron atoms, you actually see the modulation of electron probability density as caused by the quantum mechanical interference effects of this quantum corral, as they called it. One is actually imaging quantum mechanics at work. So you can imagine the effect of this tool was so astounding, and indeed STM so easy to build, that this for most people was when nanoscience came onto the horizon. This is what the first scanning tunneling microscope looked like. It consisted of transducers that could move the probe up and down in the Z direction and then bend this arm here so that the probe could scan in the X and Y direction. The idea was to set it up at some predetermined tunnel current, then scan the probe over the surface, and then, for example, when there was a step on the surface, the current would start to increase. The computer would withdraw the probe to keep the current constant, and so the step would be mapped out, with some broadening of the features owing to the finite radius of the probe. It was also pointed out in this early picture that if there was some chemical contamination on the surface that made it, for example, easier for electrons to tunnel out, then the probe would sense this as a height change too. I'm going to show you a movie that was taken in my laboratory in 1986 so you can see what an early scanning tunneling microscope looked like. The microscope is actually here. This little adjustment moves the probe up and down, and these holes here are rings of piezoelectric material that scan the tip in the X and Y direction, and then inside this, you can't see it, is a fifth element that moves the probe up and down in the Z direction, and finally a piezoelectric motor that pushes the sample towards the probe. This was taken by a visitor to my lab in 1986. I'm pointing out here the vibration isolation system, so here's the microscope, lead blocks with rubber tubing in between them, and the whole thing inside a cabinet. These are the electronics here that drive the piezoelectrics, and here that monitor the tunnel current signal and send it to a controlling computer. So pretty soon we're going to step back and see the whole system. So the whole system sat on an air table. You can see these springs here for extra vibration isolation. And Mervyn Miles is obviously impressed by lead blocks and rubber. STMs these days have much less vibration isolation. I'll zoom in again on the actual STM head. This is the air table on which the whole thing sat. These are air legs that float the table. Here, the video camera has been pointed down the ocular of a microscope, optical microscope, so you can see the probe above a graphite surface here. The lump in the foreground was an electrode connected to the graphite. This here is the electronics that causes the probe to scan in the XY direction. And this here is the electronics that senses the tunnel current and then moves the Z piezoelectric element so as to keep the height of the probe constant. The tunnel current is shown on this screen here, and down below you will see the controller that moves that piezoelectric motor to push the sample up towards the probe in small steps. So right now no current is being detected. The probe is being advanced towards the surface, and the microscope's being asked to stop the advance when a tunnel current is detected, which it was there. So a tunnel current's been detected, and what we do now is plot the correction signal applied to the piezo to keep the current constant, and then we've just stored this correction signal on a storage oscilloscope. And look at this, this is quite remarkable. You can see the features owing to atoms in the surface of graphite coming up immediately as soon as the microscope is engaged. Modern microscopes don't work as well. So from line scans like this, IBM, in particular Gerd Binnig and Heini Rohrer, managed to image the surface of a very clean silicon 111 wafer. It turns out that when this is cleaned and heated and annealed in ultra-high vacuum, it reconstructs into a very complex arrangement of surface atoms that was called the 7x7 because of the symmetry of the diffraction pattern, but the structure of which was not known. So in these STM scans, they managed to image the unit cell of the silicon 7x7. You can see the microscope only worked for a small area of the sample, and interestingly enough, even IBM did not have a computer to control their microscope. So this image was made by cutting out fragments of duplicated chart recorder scans of the surface and then gluing them together to make a 3D model, if you can believe that. Nonetheless, this 3D model caused a sensation and led to the award of the Nobel Prize in Physics to Heini Rohrer and Gerd Binnig, shared with Ernst Ruska, who invented the electron microscope.